Okay, so we're going to actually look at one more type of situation, and this is when you have a force that increases quadratically with the, or parabolically with the velocity. And you might be thinking, well, gosh, that last one was super complicated. I don't see how this could be any more complicated. And this one's actually not quite as bad. It's a little easier to work through. And I'll tell you this. Differential equations can get very complex, and there will be an entire class dedicated to them when you're in college. And fortunately, your teacher there will probably do a much better job explaining it to you than I have so far, and hopefully will make a little bit more sense to you there. Okay? But really, at the end of the day, all these problems are very similar. Okay? You just maybe have some slightly different initial conditions. So, in this case, we have, let's say that this is like some type of rocket car trying to set a world record for velocity. And when something's going really fast, it's going to have a experience a drag force that's dependent on v squared, not just v. And so let's say this car now is coasting to a stop. We're just going to use one horizontal force to make things simpler for us. And so that ma in this case would be equal to just bv squared. Okay, Fn and gravity, normal force and gravity, are acting in a different plane, so we can ignore them here. And so the only force acting in this plane would be that one. It would be negative because it's slowing it down. Okay, going opposite the direction of the velocity. And now we're going to try to figure out here if we can solve for, write a function for v. We're going to find, a function for v, a function for a. And notice that in this case, this object is slowing down. And so when acceleration is 0 is going to be when the velocity is 0 too, when it comes to a stop. Okay, so a would be equal to negative b over m times v squared. Remember that a is dv dt. Okay, so just like last time, we need to separate the variables. This time, though, it's going to be a little simpler for us because now this v term is separate from this, and so we can divide it over. So I'll divide over v squared and multiply over dt. Okay, so negative b over m dt. Okay, and so now I want to integrate both sides, this one from v naught to v, and this one from 0 to t. Okay, and so on this side right here, we just end up with negative b over m times t. On this side right here, the integral of 1 over v squared is going to be negative 1 over v. Okay, because if you take the derivative of this, you end up with that. Alright, and so we want to evaluate this from v naught to v, and so we'll have negative 1 over v minus negative 1 over v naught, and so this becomes negative 1 over v plus 1 over v naught. And we'll take that and put it right here. Okay, and we'll subtract 1 over v naught to the other side and get negative 1 over v is equal to negative b over m times t minus 1 over v naught. Let's go ahead and multiply everything by negative 1 to make everything positive. Okay, and then finally we're going to take the inverse of everything so we can solve for v. So v is equal to 1 over b over m t plus 1 over v naught. Okay, and that would be our function for velocity. Okay, and so as t gets bigger, this whole equation here is going to approach 0. When t is equal to 0, you have 1 over v naught, which is just the velocity equal to v naught. So if we graph our velocity with respect to time, it's going to look something like this. Okay. Now we want to find acceleration. So acceleration will be the derivative of this. So dv dt. Okay. And so the derivative of b over mt plus 1 over v naught is going to give us b over m t squared negative m over b times b over mt squared plus 1 over v naught. Okay, so that would be your equation for acceleration. Okay, so just a couple notes here. You'll see that when t, this piece right here, is equal to 0, then you're just left with negative m over b times 1 over v naught, or negative m over b times v naught would be your acceleration at time 0. And from there, it's going to decrease at a rate of, or it's going to look kind of like 1 over t squared, because you have a t squared down here. And so it's going to look something like this. Okay, it looks similar to your velocity graph. Before we wrap this up, I'm going to say that in this last step right here, when I find the acceleration, I think I made a mistake integrating, because if I'd done things right, then we should end up with this being squared, kind of like we started with right here. So I made a mistake going from here to here. Unfortunately, I'm not sure what it was. I'm not going to worry too much about it, because really the goal of this is to write this velocity equation, and maybe you can go back and see what my mistake was. Let me know.